Good afternoon and welcome again to the Communication and Signal Processing Seminar. Before I get started, I should again thank Shelley Feldkamp and Catherine Kate Goodwin for helping us get this seminar process going. I'm delighted to have Constantine Caramanis be our presenter today. He's a professor in the ECE department at the University of Texas at Austin. He also holds the William H. Hartig Fellowship in Electrical Engineering. He joined UT Austin ECE in the fall of 2006, and he received his AB in mathematics from Harvard University and his MS and PhD in electrical engineering computer science from MIT. His research interests center on decision-making in large-scale complex systems with a focus on learning and computation. He's interested in robust and adaptable optimization, high-dimensional statistics, and machine learning, and applications to large-scale networks, including social networks, wireless networks, transportation networks, energy networks. He also works on the applications of machine learning and optimization to computer design. So with this, I'll cede the floor to Constantine. Go ahead.
Great, thanks so much, Vijay, for inviting me, and also thanks to all the people that I met earlier today. I appreciate it. One good thing of this period is that it makes traveling easier, but hopefully we're nearing the end. So I'm going to 1 second. All right. So let's see. Okay, how does that look on your end? Everything looks okay? Yeah, please stop me. Oops. Okay, no, that's what I didn't want. Sometimes it shows that I don't want it to double up.
Yeah, now it looks good. Yeah.
Yeah, but now it's so okay. Maybe if when I go to full screen, it maybe I just need to do it manually. Because then when I do full screen, it shows two.
Yeah, it shows two of them. Yeah, that's right.
Two of them, which I don't want. Sorry, apologies for that.
It says you can share a portion of the screen.
Yeah, maybe that's better. But I'll just try going directly from Google Slides. So maybe that will be. That should be okay. I thought maybe PDF would have been easier. Okay. All right, one more time here. Okay, so
You're looking for the present thing? Yeah, present.
Yeah.
Yeah, you can either, I mean, present mode is that.
Yeah. Okay. Yeah. No, this is great. Well, thanks. So thanks again, Vijay and everyone. So I've been working actually like many other people in the audience on mixture problems and EM for a number of years. And the story that I'm going to tell you today is the culmination of some of these and some of the most recent thoughts. Primarily, this is going to be work jointly with Jong-Yel Kwon, who's a PhD student working with me at University of Texas at Austin, and I'll be talking about some general results for mixture problems of log concave densities, though I almost always have in mind, and my pictures will show this, mixtures of Gaussians and mixtures of linear regression. So I'll specialize to those, and actually even the way that I state some of these results, even though it's possible to state them with a little bit more generality, these have really been our motivating examples. So just a few words about mixture models. I'm not going to talk much about applications here, but the mixture models are an appealing way to think about using small building blocks to create some more intricate or more interesting statistical models, and so they're appealing, and different ways of thinking about how to build up interesting models from simpler building blocks is always interesting. And I want to mention one that, again, also many people here have thought about extensively, and that is via addition. So this is building up using superposition, and there's lots of types of problems we think about in this sense. So for example, multitask learning is often treated by trying to recover a variable that can be modeled as block sparse plus sparse. We spent some years, we meaning the community, and continue to do so, thinking about robust PCA modeled as a low rank matrix plus a sparse matrix, and various variants of this problem, and have interesting applications. So we could think about robust PCA, or even robust matrix completion, robust recommendation, modeling robust recommendation, and collaborative filtering by low rank plus sparse plus column sparse. And my 30,000 foot view of one of the reasons that we have been successful in treating all of these problems is that there is a key, even though these problems are not convex as written, sparsity, low rank, these aren't convex constraints, checking whether S plus B or L plus S or L plus S plus C equals or is close to the data that you have, that actually is a convex operation. And that has been, I think, at the core of the mathematical success of using tools from convex optimization for all of these problems. And this is, in my view, why changing this superposition model to instead of a plus, making this an or, which is really what is at the core of a mixture. We get data, and the data came either from this model or from that model, is so difficult. Even though we can still check, if someone were to give you solutions, you have a mixture of linear regressions, and some kind person gives you the solution, say that the two regressors are either beta 1 or beta 2, then we could go through every point and check, does it seem like this point is fit well by beta 1 or by beta 2, and so on. That operation is not something that's easily encoded into a convex optimization problem. And I see that as one intuitive explanation for why mixtures have been so challenging, and why we end up having to take this convexification approach, which is the core of the EM algorithm, to try to address these problems. Okay, so the two key problems I have in mind is the mixture of K Gaussians. So this is a little toy picture of it. In this case, you're seeing 4 very well separated centers with Gaussian points around them. The goal is to find the centers. Or a mixture of K linear regressions. This is actually this is an interesting problem because it's been considered from a number of different viewpoints and under a number of different names. So just to point out that actually mixed regression is a subspace clustering problem, but we don't think of it as subspace clustering because all of the tools that we've developed from subspace clustering, again, like Laura and others have spent time thinking about these things and have a lot of the state-of-the-art results, are really not about the setting. They're not really about clustering codimension 1 subspaces, but rather clustering a large number of lower dimensional subspaces. And then it's also just worth noting that this is that mixture of linear regression is related to phase retrieval. If you think about the k equals 2 setting, where you're clustering, where you're trying to compute beta and minus beta, those are the two regressors. Each sample comes is generated according to a regressor beta or minus beta, that's exactly akin to erasing sign information. So it's also very related to this problem that many have spent time looking at. So in this talk, what I'm interested in are primarily two questions, and one is I'm looking at the low signal to noise ratio, and I'm interested in understanding what are the fundamental statistical limits for parameter recovery in this low SNR setting, and of course I'll define exactly what that means. And then a second question, which a priori isn't related, but turns out to be very related, is what can we say about the EM algorithm? And I have a slide on to remind us exactly what EM does, but these are on their face separate questions, but actually the answer to this to both end up being related, at least in our approach. So again, I'm focusing, though my previous slides showed very small k. That's really just because that's all I can draw. But really, I'm interested in the setting where k, the number of things that I'm mixing, grows to be very large. That said, let me give a small indication that in the low SNR regime already things are different for mixtures than we would expect them, perhaps would expect them to be. And I just want to give this brief anecdote, and actually let's think about this, one of the simplest problems, which is linear regression with Gaussian noise. So the model is the first displayed line here, y equals x beta plus noise. You can think of x being Gaussian and e being Gaussian, whatever the nicest setting you like. And beta is what we wish to compute. So, I wrote down what our least squares estimator would be. And in this case, we know that the error rate, the statistical rate that we get from this algorithm, which is also minimax optimal, is what's on the bottom. So we have beta hat minus beta goes like sigma, which is the variance of the noise E, times root d over n. The key point here is that this rate of convergence doesn't change as sigma grows. In other words, keeping everything else fixed, here we might consider a reasonable notion of signal to noise ratio to be the magnitude of beta would be our signal strength versus the magnitude of sigma, that would be our noise strength. And even as that ratio becomes very, very small, the error rate here, the rate of convergence remains the same, square root of d over n. We need 4 times the number of points if we want to cut our error in half. But already for a mixture of two linear regressions, again with all of the nicest assumptions that we can make, Gaussian noise, etc., this ceases to be the case. So let me parse this from you. This is from some work a few years ago with 2 former students of mine, Xinyang Yi and Yudong Chen. Yudong is a professor at Cornell right now. So the model is, again, y equals, every point I get is generated either from regressor beta 1 or beta 2. I see y equals x beta 1 or y equals x beta 2. And just to parse this here, when I'm in the very high SNR regime, so you can think of that as meaning that sigma is very, very small compared to the size of beta. Basically, terms B and C are dominated by term A. And so our loss looks like, again, up to some log factors that I think are more a factor of the analysis than of something fundamental. The key thing I want to focus on is that, again, we have this sigma. Whoops, I see here I switched my notation for dimension. Instead of D, I made it a P. But P is now the dimension. I have sigma square root of P over N. So in the high SNR regime, we recover the parametric rate. However, when sigma becomes very big, or equivalently when the norm of beta 1 and beta 2 become very, very small, you see that it's term C here that ends up dominating, on the right-hand side, which means that the rate, unlike linear convergence, the rate actually changes. It becomes, statistically speaking, a fundamentally harder problem. So already we see that there's an indication that interesting things are happening when we're looking at low versus high SNR regimes. Basically, statistical effects that just aren't present in some of the standard problems like linear regression. I'm going to say a lot more about Gaussian mixtures in low SNR, but the picture we should have in mind is that as we go from high SNR to low SNR, you see what happens is that this overlap becomes fundamentally challenging because in this high SNR problem, it's not at all surprising that we would recover a parametric rate because there is no leakage or there's no cross-contamination. None of the darts intended for this center end up falling near that one. So that is a simple idea. But of course, in the very low SNR regime, which you can think of as the centers coming very close together, which is equivalent to the blowing up the variance of each Gaussian, the picture looks very different. Okay, so let me now summarize what I know about this problem, specifically about Gaussian mixtures. Again, this is a problem that has been studied for many years. I'm going to tell you about what I know about Gaussian mixtures, and also what I know about the EM algorithm in terms of solving this problem, and specifically in terms of what kind of recovery guarantees or statistical performance you can hope for as the SNR becomes small. Now again, what is the notion of SNR that makes sense for Gaussian mixtures? It would be a ratio of how big these individual how much noise there is compared to how far apart the centers are. So we'll just fix for now, for our discussion, the variance for each Gaussian to be 1, and so that leaves us with the distance between the means as being our notion of signal to noise ratio. So here on this blue axis running from left to right, excuse me, I have I'm using that to represent the signal to noise ratio. D is the dimension. So far on the left is when I have basically order 1, or possibly even, we could even imagine even lower separation between the means, and that has been looked at. And then way on the right, I have a polynomial in K, or even polynomial in D separation. Now, I wrote square root of D to the right of square root of K just because the result came first and was improved to go from root D to root K or root...
Sorry, I'm having trouble hearing you.
Siri thinks I'm talking to her. Sorry. But really, in many cases, K, we might want to think of K as being even bigger than D, as was the picture on the previous slide. So first, in terms of negative results for very, very small separation, Moitra and Valiant about 10 years ago showed that if you have very small separation, so a constant order separation, as K grows, you're going to have to pay an exponential price in sample complexity. So something else that I want to be clear about in this talk, most of our results are about sample complexity, not computational complexity, and I'll revisit that, but that's something to keep in mind. So Moitra and Valiant, and then again Hart and Price, proved this lower bound, this exponential lower bound on the sample complexity when we have this order 1 separation. And then more recently, Heinrich and Kahn showed a lower bound on the rate that you can get as well. Now on the positive side, prior to that, Dasgupta in '99 had looked at the setting where d is bigger than k, and looked at the setting where the separation is about square root of d apart. So this is a very large SNR setting, and was the first to give a polynomial time and sample complexity algorithm for recovering the means to arbitrary precision for Gaussian mixtures. And this was improved to d to the 1/4 in Dasgupta and Schulman. And then, several years after that, Van Paula and Wang looked at the setting where potentially you have a where k is where the convergence rate is k. I'm sorry, where the sample complexity is k to the 1/4, and therefore by improving the square root of d result. Now let's fast forward a few years to just a couple years ago, and a sequence of papers gave what are essentially still state-of-the-art results in terms of both computation and sample complexity. So these results by these three sets of authors here essentially establish that if you have k to the 1/gamma separation, then with k to the gamma, or polynomial of that, k to the gamma sample complexity and algorithmic complexity, computational complexity, you can recover the parameters of the problem. So now you're probably wondering, unless you already know, what is this alluring line here that is indicated, the square root log k. And right around the same time, Regev and Vijayaraghavan showed that there's a phase transition where the separation reaches root log k. So, and they showed that below root log k, you need exponential samples. And essentially, what they showed is that there are two distributions that have the required, two mixtures of Gaussians that have a very low total variation distance. So in other words, without exponentially many samples, are indistinguishable from each other, yet have high enough separation of the means. High enough being, just to the left of this line. And on the flip side, they showed that as long as you're to the right of this line, it's possible with exponential, potentially, computational effort, but with polynomial samples to compute the parameters. Okay, so this line essentially represents, if we're interested in sample complexity, this is the dividing line between something that's polynomially learnable, and again, I'm talking about parameter estimation. I'm not talking about some other sense. I want to compute the parameters. I want to compute the centers of the Gaussians. And then to the left of this line, we need a super polynomial number of samples. And so this result by Regev and Vijayaraghavan gives a polynomial, somewhat large polynomial in K and D in the number of Gaussians and in the dimension of the number of how many samples you need. And one other thing I want to now point out is that, again, in fairly recent work, Jan and Yin and Sarkar showed that if we have separation square root of k, the EM algorithm, if well initialized, is able to converge. So the way that I've presented them, these are somewhat disjoint results, because the EM algorithm is of interest on its own, but it's not what is necessarily used to achieve any of these results in here. But nevertheless, this root k result is interesting because it tells us, it sheds light on when does EM succeed, and we can see that as an improvement of the Dasgupta and Schulman had a very EM-like algorithm that to solve this clustering problem in contrast to this work of Impala and Wang, which had a polynomial time algorithm, but wasn't EM. Okay, so in this context, let me tell you the part of the punchline of this talk, which is specific for Gaussians. So in this regime where we have separation square root log k, which is this critical regime, and we prove essentially two things. So first, we show on the sample complexity front that k d over epsilon squared, which is information theoretically the minimum that you would need, is also sufficient for learning the parameters. And so this, I didn't write down the polynomial that Regev and Vijay-Raghavan have, but that's in comparison to this polynomial. So this is exactly characterizes the sample complexity of this problem at this critical phase transition. And again, this is a result about sample complexity in contrast to this set of results here. If we try to make k to the 1 over gamma equal square root log k, then we're going to get something like poly of k to the log k sample complexity. So compared to that, we have linear complexity, which is optimal. On the other hand, though, our algorithm, this is not an algorithmic result. It's not an algorithmic result because, similar to the Regev and Vijay-Raghavan work, we require good initialization, which is not easily obtainable by, as far as we know, by a polynomial time algorithm. So this relates to some future directions, which I think are interesting, and I'll mention at the end. But as far as we know, we require exponential computational effort in order to initialize well enough for this local result to hold. And what is the local result? The local result is that EM will succeed if initialized well with this number of samples, kd over epsilon squared samples. So that means that, so this improves over this root k result and shows that EM doesn't in fact need root k separation. Root log k is enough. And this links these two results because actually, in fact, for the sample complexity result, we use the result of EM. So so EM can be used to obtain that. And then also, as I'll show you, in terms of the statistical rate, it gets minimax rates, which is again going to be the parametric rate for this particular problem. If there are any questions at any point, feel free to interrupt me.
I'll just ask a quick one here. So are we still these different Gaussian modes or whatever are equally probable here, or similar variances? Because
very good question. Yes. So yes. So I'm going to give a little more detail. Good. Thank you. I meant to say a few things about that, and I forgot. So one important assumption, which we don't know our way around, is that the covariance is a scalar multiple of the identity for all of these.
Okay. Now,
probably if it's a scalar multiple of the same covariance, we could probably do something about that. Mm-hmm. We can address the setting where they are different scalar multiples, so they have different variances. So that is actually something that is another innovation, let's say, that our analysis gives us compared to the Regev and Vijay-Raghavan work. And also, they don't need to be the mixtures don't need to be balanced.
Okay.
We do assume that they are so in the bounds. This k is not actually k. It's 1 over the smallest probability.
Okay, that makes sense. Yeah.
Yeah, and also you can't really do better than that, because you would just have to, if regardless of what k is, if any particular sample is you only get only 1 out of 100 points are there, you need to wait for 100 times however many points you need for that center.
Right.
Each center requires d over epsilon squared, so you really can't get away with anything less than 1 over the smallest probability. But yeah, but for simplicity, I just called it k.
Thank you.
I
I
think
just have another question about the assumptions. So this is all for Gaussian mixtures. If you do something simple like truncated Gaussian, so now the tails are finite, do you get better rates? One would assume that you should, right?
I mean, even if something is so, even if you were to give me the labels and I have just anything that's sub-Gaussian, I don't think I will get something that's much better than this unless I'm radically unless I'm changing the variance. So there's no
right.
So the tails of the Gaussian aren't really going to generate too much of a problem for me. Let me make a mention.
But just from a sphere packing argument, right? You should be able to. I mean, let's say all of the supports were the same, and they're on a disk, right? And then you have perfect separability.
That's a good point. That's a good point.
And,
yep.
Yeah.
I take
So
that
you
back.
should be able to go much lower than k to the 1/4, for example.
So you're right. If there is no overlap, and I'll in some of the details, exactly what you bring up is what we need to. What we're worried about is how much cross contamination there is.
Right.
So if you are in a regime where you can clip that, but yeah, so that you're right. You're right. If you could truncate that to an order 1 number of standard deviations,
Yeah.
then should be able to do what? Let's see. I mean, again, you're not going to beat KD.
You're not going to beat log k, right? Yeah.
Because KD over epsilon squared is as if
Right.
someone just tells you what the labels are of each point. So it probably is
Maybe
that
the dth root of k. You probably could do the dth root of k on this axis. So as d gets large, that goes to log k, right?
yeah, that's
Right.
so that could be. It could also be that it helps you on the computational side, because you're not going to be in a situation where you have, like this, where you really can't tell
Right.
what's happening. And basically, the initialization is it's just a brute force epsilon net argument, where and perhaps you wouldn't need that. Maybe there's something better that you can do.
Okay. Cool. Thank you. I didn't want to derail you on that. But...
No, yeah, it's a very good.
Yeah.
I'm sorry, I can't see the names of who's talking.
I'm Al Hero. Sorry.
Yeah, thanks, Al.
Yeah.
I tried somehow. I think there's some Zoom setting that. But
yeah.
Okay. So a few. I guess I'll try to wrap up in about 15 minutes, if that's okay, VJ.
Yeah, that's fine. Yeah.
So I should tell you what the model is, and again remind us what that EM algorithm is, and then tell you a few facets of this story, which we're excited about. Okay, so I think this is fairly standard. One other tangent I want to mention is that another very interesting problem is when you don't know K, and that especially when you don't know K and you're in the low SNR setting, I think it's a quite interesting problem. But here we're assuming that we do know K and it is correct. So this is our mixture problem. This is the pi k are we can just think of them as all being 1 over k if we like, though again we're able to estimate those as well. And now in the Gaussian mixture problem, each p of x colon theta k is a Gaussian with center theta k. So the thetas in this case are what I want to estimate. Again, more generally, we could say what we want to estimate are the pi's and the thetas and the variances. But for this talk, let's let the sigmas all be equal to 1 and or all the same in any case, and the pi's just be balanced, give a balanced distribution. So some things that I assume are a little bit of regularity on p, the distribution of the individual. I need it to be log concave, and also I'm asking that I can compute second derivatives. And in part, that's because of the results I want to look at in addition to EM, in addition to the sample complexity and statistical rate results. I want to another link that we found is just to the landscape, the local landscape of the log likelihood distribution. Sorry, function. So the two examples I have in mind are, again, spherical Gaussians. In that case, the log likelihood of every individual model is minus a quadratic. And then linear regression with Gaussian noise, the log likelihood of each individual model again looks like this. This is Gaussian noise and Gaussian design. So these are the primarily the two examples I have in mind. So in terms of mixture models, we'd like to do max likelihood estimation. The log likelihood is the log of what I showed before. For two components, when k is equal to 2, there is hope for global convergence in certain cases, though there's not a general theory that I'm aware of. So the Skalakis and Zamos and Zabetakis in 2017 showed that you can get global convergence of EM from a random initialization point, in other words, for Gaussian mixtures. And then again with Zhongyol, and then in collaboration with Chan, and this is Yudong Chen and Damek Davis at Cornell, we showed that you can do the same for mixed regression. And though there are some similar ideas, it would be interesting to have a more general result about what the global landscape looks like of this function when k is equal to 2. When k is equal to 3 or more, we know that already in the setting of Gaussian mixtures, we can't hope for global convergence results because the log likelihood has non-spurious local minima. And this is a recent result by Jin, Zhang, Balakrishnan, Wainwright, and Jordan. So in other words, we need to separate initialization and whatever algorithmic approach we're going to take. Okay, again, I'm mostly focused on regression and even more so on Gaussian mixtures, but it's possible to parameterize, to talk about what good separation or SNR means, and it essentially means that if I give you a point, you have a reasonable chance of guessing where it came from. And so that's really what this says. This is saying that the probability that the probability under the ith model, so if it's the ith center, that the likelihood of a point with respect to some other different from I model is bigger than the true model, now that is small. So that's essentially what this says. For a mixture of Gaussians, again, if we fix the size of the variance, this just has to do with how far apart the centers are, and our assumption throughout is going to be that the centers are at least this root log k, have this root log k separation. So if I say well separated, I don't mean that they're very separated. I mean that they're separated enough so that polynomial learnability is possible. And for regressions, I need actually a little bit bigger. I need something that scales in k, and this is the best that we're aware of. But we think that this is the right number that corresponds to root log k. But though though perhaps not 100% clear on that yet. So this is what I mean by well separated. So what does EM do? Essentially, EM has two steps. In the first step, it gives a soft guess of what the labels are. In other words, it basically computes a posterior on the distribution of the label for every single point. It looks at a point and it says, I think the likelihood that it came from I is this, the likelihood that it came from J is that. And I'll be defining this notation, but it's really this W that is gonna represent this this likelihood, and I'll show you in a slide what that is. And then once you have those, we update in the M step the parameter that maximizes our likelihood estimate. I'll be just referring to this as the M step, and that is really just maximizing this, and this for any model where P is log concave, the log of that is concave. So this is concave, and now we just have a mixture of concave things, and hence it's concave. So maximizing over this argument theta is something easy, which is why we do EM to begin with. So the first part of the story is that sufficient conditions that guarantee that EM locally converges also guarantee that the log likelihood function is locally strongly concave. So what this shows, and also these are the sufficient conditions that get us the minimax optimal rate and get us the information theoretically optimal sample complexity for the case of Gaussian mixtures. So I'm not saying that one implies the other, but I'm saying that sufficient conditions, there's one set of sufficient conditions that essentially guarantees both. And those sufficient conditions are that you have that right number of samples, and that you have that minimum separation to call them well separated. Okay, so a little bit of notation here, but we don't need to parse all of this. Just one thing to keep in mind is this WI is the posterior. So if you have a particular model theta, then this is just your posterior estimate that any given point X came from model I. So this is what WI is. It's the likelihood that a particular point came from model I. And these are the derivatives and second derivatives of the log likelihood function. And I just want us to just look at this form of WI times the Hessian or this other term later in the line. We're going to see those again. And basically the point here is to remember that is what relates to the second order information. So it relates to the Hessian. And what we're going to try to do is show that this Hessian is concave. Okay, now to the EM algorithm. A key step for showing the convergence of the EM algorithm is controlling this top quantity here. Now, I'm not going to go through all of the details. This has now been around for quite some time. But some intuition, if you haven't looked at this Balakrishnan Wainwright Yu paper or others following up in that vein, the intuition is if you remember your analysis for gradient descent for a strongly convex function, and you think about how you show that it has linear convergence. What's happening with the main difference? Obviously, we want to exploit something similar because we know that Q is assumed to be strongly concave. We're maximizing Q. It inherits that from the log concavity of the individual functions, individual distributions, and we'd like to exploit that log concave in order to prove that EM or some gradient-like algorithm has a linear convergence. The problem is that we're updating theta while we're doing the E step and the M step. So in other words, we're doing EM not always with respect to the optimal parameter theta star. And so you need the stability of this gradient that would come up if you tried to mirror the analysis of gradient descent for a strongly convex function. And so, being able to control that difference, upper bound it by the difference between theta and theta star, is again like very similar to the power that strong convexity gives us in gradient analysis compared to, say, a function that's just smooth, where we don't have control of this nature. So that's at a high level why we need something like this. But for those of you that know, EM is basically requires us to control this this term. And so if we look at this term here, again, I just chose a few sample terms here, but I'm not showing you all the details, but essentially the diagonal blocks, maybe this picture is the best to show. This is the Hessian of the log likelihood function, and HIIs are the diagonal blocks, and HIJs are the off diagonal blocks. The HIJs and HIIs that have to do with the Hessian of the log likelihood are very close to, very related to the Hessian and second derivatives of this Q function, which is our estimate for the likelihood. And by relating these two and showing that they're not far apart, we can essentially show that if this matrix here, the Hessian of the log likelihood function is concave. Sorry, I didn't mean to say it that way. We can show a sufficient condition that shows that this matrix is concave, either for the h's that come from the log likelihood or from the h's that come from the analysis of EM. And the argument for showing this is actually, surprisingly perhaps, fairly coarse. It's really just a diagonal dominance argument. So it's showing that these blocks are very big and all of the off-diagonal blocks are very small. And so showing that then basically gets us two birds with one stone if we can show that what I've denoted as HII tilde and HIK tilde, these are the second derivatives that come from the Q function, are very close enough to the blocks of the Hessian of the log likelihood. And indeed, it turns out to be the case. And so basically there's just one diagonal dominance argument that we need to show that gets us two things at once. First, it guarantees linear convergence for EM, and it also guarantees that the landscape is locally concave, which means that you could use any first order algorithm and also enjoy the consequence of that concavity. It's not something necessarily special about EM. And what I find interesting about this is that though it's a coarse argument, it is enough to get us to that information theoretic limit in terms of sample complexity or minimax optimality for the rates. Okay, so I want to give you at least one kind of technical idea of what we need. So I may skip a few things here. What this slide is saying is that, in terms of the technical roadmap, we would like to show diagonal dominance for the population model, and then we somehow need to move from population model to finite sample model. And there's two ways to do that. One possible approach, which we don't take, is to try to say that the finite sample approach is close enough to the population. But a more direct approach is just finding the right concentration arguments for the finite sample versions of everything. So the idea in a picture is pretty simple, and it basically has to do with controlling this cross-contamination, which comes from things being too close. And the reason I wanted to focus on this quantity that I highlighted or bolded before, or put a box around before, is that it's this cross-contamination really looks like this expectation with respect to the kth component of the ith quantity. This is kind of like the IK block. in the diagonal dominance argument. And the key to obtaining good concentration arguments is being able to break apart the good and the bad events. A good event is that a sample that came from the cave component ended up being much closer to the cave component than to the ith component. And a bad, and conversely, that the bad event is that doesn't happen. So the intuition is pretty simple, and it's that bad events can have a big impact on your calculation, but fortunately they're quite rare, which means that they're not going to be very many of these. And it's really this delicate balance between those two things, which is what we need to do. Okay, so this is the sample complexity. I want to skip to, okay, I guess I'm not skipping too much, to this, the statistical rate. So the statistical rate, what I'm interested in is how quickly is theta n, my EM, the optimization for my what EM converges to, how quickly is that going to converge to theta star? So again, what I've kind of zipped through so far is that because we have this diagonal dominance argument, EM converges linearly. It converges linearly to theta n star, not to theta star. And so what I want to know is how quickly does theta n star converge to theta star? So looking at this inequality here, this is just triangle inequality is the first step. So it's saying that the distance, I could have just used a norm, the distance between theta n star, the finite sample, and the population optimal is bounded in this way. And then you see I have the same quantity on the right and the same quantity as the first term on the left. Alpha is some number less than 1. In our analysis, it's 1 over root 3, but it doesn't really matter what it is as long as it's small enough. The point is that by rearranging these terms, we see that you can understand the statistical rate by doing the following. Look at the population optimal, theta star, and apply one step of finite sample EM and ask, how far did that move me away? And if you can control that one step of EM only at one single point, at theta star, then that exactly gives you the statistical rate. So this is what, in a very simple way, this equation gives us. The only thing that requires work to get to this equation is a second inequality, which is basically saying that we have a contraction, that locally the EM step is a contraction. That's what this, and we had to work to show that. That's what the diagonal dominance gives us. This first is just the triangle inequality. Okay, so we haven't learned much so far other than the fact that a key to understanding the quantity I want, how close is theta n star to theta star, is controlled by how much does one step of finite sample EM move me away from my population optimal. And maybe if there's kind of one technical nugget I will leave you with in terms of what we actually had to do to make some of this work is, and if I may just look at this a little more carefully here, and then I won't go over too much, let's look at this quantity. So let's look at the difference between, here on the left, the difference between theta star and how far away from theta star one step of EM gives me. Okay, so I wrote that out with a minus sign here. Theta star, and this is one step of finite sample EM. How far does that? And if this is not a hard calculation for, say, for Gaussian mixtures, if you write out what the M step gives us, it looks like this. Okay, so again, xi's are my samples, and I just chose a particular center here, one of the centers. Now we can think, okay, everything seems to be Gaussian or sub-Gaussian, so maybe I can just bound this directly. But that's going to be a big problem, because if we bound this directly, then then that's not going to work out very well, because some of the xi's didn't come from center 1 here. And so the best that I can do in terms of bounding this is going to look like the difference between whatever center xi did come from, and center 1. In other words, this quantity here can be very big. It's not something that necessarily is going to be that we can control and going to 0. So we need some different idea. And this is again just comes to I'm going to show you just a simple different way to write a concentration inequality that comes from taking advantage of the fact that I have good events and bad events. So here's stated a little bit more generally. If I have a bunch of events that are disjoint and their union is everything, and x is a random variable, maybe I should have chosen z just to be different. It doesn't have to. It's not this x necessarily. X is any random variable, and now I'm writing its sub-Gaussian norm. AI is the sub-Gaussian norm of x if I know it happened to fall in event AI. Some of these will be big, some of these could be small. Now let's see how many of the x's, if I have n IID samples from x, x1, x2, up to xn, some of them fell in A1, some of them fell in A2, some of them fell in AM. And ni is the number of samples from both. Then this quantity here, which just flipping back one slide, is exactly what I essentially want to compute here. This quantity here, which is like a deviation from the mean, I can bound it by counting up the number of x's that fell in each one of these disjoint events. This is really, it builds off of the union bound. There are some technical details that are required here, but I think at that level it shouldn't be a shocking thing to see. But shocking at a different level, perhaps, it was incredibly useful, and actually maybe was like the one technical key which gave us improvements with respect to prior work. So I'm trying to bully you into believing that this was an important step by saying that. But in any case, this really was the key for us. And how do we use it? We use it again by virtue of the fact that we have good events and bad events, and the bad events are controlled by virtue of good initialization and because we're starting close. So what are the good events for us? The good events are that the sample is very close to the true mean, in which case this difference here is very small. And the bad events are that difference is big, but in that case there's only very few of those. And so that is explicitly captured here. So when you have a good event, you've got lots of those, but its norm is very, very small. Its deviation from the mean that you want is very, very small. And similarly for the bad events. So that was the main part of the story that I want to say. I think that there are still some interesting algorithmic questions that are intriguing, that are open. And namely, is the work that I mentioned by Diakonikolas and co-authors and those three groups that I mentioned, are those is that complexity, which is super polynomial, if you take their work and specialize it to this root log k separation, is that fundamental? My personal guess is that it probably is. I think it probably is, but that still leaves open some other interesting questions if we're in a setting where, for example, we have some labels. So something that I'm currently thinking about is the setting where you might have labels only from one sample and only wish to recover that one sample. That doesn't violate any other negative results, but that would be interesting. And also, when you have, I'm currently interested in settings where you have dynamics in mixture models, so mixtures of MDPs that allow some advantages to be able to see a trajectory of from a certain model, but of course it has other interesting challenges. So thanks very much for the attention, and I'm always happy for any follow-up. I've been interested in this problem for quite some time, and I'm eager to hear what others are working on and what's next.
So Clay had his hand up, but Clay, let me first finish off. I'll do the discussion, and then maybe you can ask the question after that. So if you want to stop sharing, I'll just share just a few. I have just a few simple thoughts. Oops. So yeah, first, thanks again for, so you can see my slide, right? Yeah.
Yes.
All right, so thanks again for an excellent talk, and I think it stimulated a lot of questions, so that was great. So I'll skip this part a little bit. The overview, I think you summarized it very well at the end, so I don't need to go back. So I had a few sort of thoughts and questions. So the sort of thoughts go on to actually the second half of this. So at a high level, the results seem to need good separation. And what happens in practice if you don't have it? So does the EM algorithm crash and burn, or?
Yeah, I think it crashes and burns. I think if you're too close, it's not going to work. There's another line of work that I didn't mention that treats the setting where you have additional assumptions on where the means are. So for example, if they're all linearly independent, then you can also use tensor methods. There's a whole list of authors, Anima, and I'm sorry, now that I'm being recorded, I probably shouldn't just give partial author lists, but there's a lot of work in that direction, which is interesting, and works very well when you have when you don't have separation. So you can replace separation assumptions with others, but when those go away, then you're sort of back to this picture.
All right, thanks. So the next thing was, you alluded to this part at the end, was in the Gaussian mixture model. It seems like you can hit the separation lower bound, but in the linear regression case, the results seem to indicate you need much greater separation. What is the intuition behind it? And I mean, is that a conjectured lower bound? And the theory just needs to catch up. Yeah.
I mean, so you are estimating more. I was going to say you're not estimating more parameters, but every sample you're getting is you get basically a one-dimensional sample because you're getting a projection. Well, my guess would be that you do need this linear separation, but I'm not sure that's certainly it. But that would be my guess. That you need
thanks.
that
Yeah.
linear.
So the next two questions are sort of related, and this is the way I was sort of reading your analysis. So you first look at the EM operator. This is in the population setting, and then you sort of analyze properties of that. And you're showing it's locally basically a contraction, and the separation basically says you have that property. And good initialization would say, okay, you're within that place where the contraction holds, so you will basically go stick to the optimal solution there. And in the second part, you sort of, it's more sophisticated than that, but in some sense, you're showing that with independent samples in each iteration, the empirical operator is close enough to the EM operator, so things work out nicely in some sense. But the analysis does need independent samples at each step. I was wondering, why not take so it seems like if you take something like an old stochastic approximation scheme, especially Robbins-Monroe, for example, so I sort of smoothly change my estimates. I'd still take a maximization, but then I change it based on, I just take a convex combination from the previous thing. I should be able to generalize a lot of the results because it just depends on the ODE behavior, and it seems like you have local contraction. So this ODE is well behaved if you start in the local point. So you should be able to even generalize to martingale difference noises and maybe even get better sense with Lyapunov stability results and linearization on the point of fixed point of interest. And this sort of idea I was thinking might even generalize to other distributions and not necessarily stick with Gaussianity or But this is just a thought that I had of going forward from what you had
Yeah.
stopped sharing.
So that would be what? That would be like a setting where you're getting points one at a time.
Yeah. So in your case, you had n points, and you sort of had t steps you want to take it, and you had n over t samples, and every time you were sort of, they had to be independent. But even if it was independent, you could think of these points either one at a time, or in some means you could generalize to that. Right?
Yeah, I think that's interesting. Now, your question about whether you could maybe I guess my thinking would be
I mean, the reason I was coming at it is because stochastic approximation is trying to compute a fixed point, but you just have empirical operators. Why not go the whole way and use that methodology to study it?
Yeah. So I think, as I mentioned, I can't remember if in our original paper, what I presented as something is basically our more recent rethinking of last year's Colt, of the 2020 Colt paper on which basically is which I had sent you, Vijay, anyway, so currently we're not trying to couple it to the population model, but on the other hand, we are using we are essentially trying to establish this overall convexity argument, or concavity in this case, local concavity. So yeah, I'm not sure. It's a good question. I don't know what happens if you lose independence from each sample, and how basically the key to this argument is what I was mentioning at the end, which is separating these good events and bad events and trying to show a concentration among those. But I can't think of why. Yeah, maybe perhaps a martingale argument would be enough to.
Anyway, this is just a thought. So Clay, you had a question. Please go ahead. Sorry. Yeah. Didn't want to.
Yeah, Constantine, thanks for a nice talk. And I was just curious, could you say more about the how accurate the initialization needs to be to get the linear convergence?
Yeah, so the initialization needs to be order 1 accurate. So in other words, it needs to be, you need to initialize to within to an order 1 quantity of the magnitude of the difference of the means.
Okay.
Yeah, so we actually use a quarter is the number that we have, but that's how close you would need to be.
I guess this is kind of maybe I'm reaching here, but there's you can think of k-means as a limiting case of a Gaussian mixture model, especially with isotropic covariances. Does your theory say anything about k-means? And I'm thinking in particular, there's some methods for initializing k-means, like k-means plus plus and extensions.
That's a good question. I first started actually working on these models by looking at the zero noise setting for mixed linear regression, in which case EM basically becomes like a k-means type algorithm, because then you're making hard guesses. Yeah, I think that I don't know. I'm not sure. I don't know what would happen. I don't know about, so k-means plus plus. Does that help you if things are very close together?
Yeah, I don't know the details of that work. So
yeah, but it's certainly interesting to think about that.
Any other questions? Yeah. Floor is open. I guess there aren't any. So, Constantine, thanks again for an excellent talk.
Thanks, Vijay, and thanks everyone. Yeah, it's great talking to everyone, and appreciated the questions during the talk too.
And this video should be up in some time, maybe day tomorrow or day after, or whatever.
Okay.
All right, great. Thanks.
Bye, everyone.
Bye.